Okay, so we want to find the moment of inertia of this ellipsoid with this density function. Okay, so you start partitioning. You choose to partition on your Z. Choose the fixed limits to be on Z. You could use X or Y. X could go from 0 to 1, or -1 to 1. Y could go from -2 to 2, okay? Or Z could go from -3 to 3. Now, if they all do that, you get this rectangular box, which is not your ellipsoid, right? But your ellipsoid is within this box. And it hits the X, Y, and Z axes, okay, on these planes. Now, I'm not going to even attempt to draw the ellipsoid because we know what that looks like, okay? But I want to confine ourselves to one partition here, okay? So your partition starts with -3 equals Z0 less than Z1 less than, and then we have a typical Z sub I minus 1 and a Z sub I and a Z sub n, which equals 3, right? So we have a typical interval. Now what we want to do is partition this so that a typical point, xi star, yi star, zi star, yi star, doing it in the order you chose to do it because you did y next, and then you did x, okay? And let's just see where we're going. Why are we doing this partition? We're trying to find the typical volume increment, okay? And what we're doing is we're going to end up by locating the general point xk star, yj star, ci star, okay, in its volume increment. Okay, so if we keep in mind that this is what we're trying to do, what's our next partition? Well, let's just look geometrically. We're going to have a typical Zi star within this interval, right? Between Zi minus 1 and Zi. So we'll take that typical Z sub I star and hold it fixed and see what shape we have, okay? Well, clearly, as we understand, because we understand the surface pretty well, this confines us to the Z equals Z sub I plane. Confining ourselves to the Z equals Z sub I plane, we get an ellipse. Now, we need to know what the equation of that ellipse is. Okay, so what we have is an ellipse. It's going to be geometrically similar to the ellipse we would have if we let Z equals 0. Okay? So it's going to have twice the semi-axes in the y direction as it does in the x direction. It's going to have about this shape, something like that. Okay? What is the equation of this ellipse? Okay, we want to write that down. We want to draw this picture, we want to draw this picture. If we're good enough at drawing, maybe we draw the ellipsoid in there. Lots of luck. Okay? It doesn't have to be a great picture, but it has to be indicative. Okay, so anyhow, what's your equation? Your equation is x squared plus y squared over 4 plus z sub I star squared over 9 equals 1. Okay? And now z sub I star is some fixed, whatever the coordinate is that we're trying to find, right? It's just an arbitrary coordinate. An arbitrary z coordinate between -3 and 3. So we have x squared plus y squared over 4 equals 1 minus zi squared star squared over 9. Okay? Well, this is less than 1. We would officially want to divide through everything by this quantity to get this equal to 1. But if we understand ellipses, we understand when this number gets smaller, the ellipse gets smaller. Okay? Because we would normalize it by dividing by a smaller number, ending up with a smaller denominator under each of these terms. Okay? Which would give us a smaller axis. And of course, we understand ellipses from what we did much earlier in the course. Okay, so we have this and we say this is a smaller ellipse. We don't really need to know that, but if we want to think about what's going on, it's something we do really want to know. We don't need to know that in order to set up the inequalities. We don't need to know that this is smaller than the ellipse you get in the xy plane. But we should understand why. Okay, well, anyhow. So now what do? Well, we're going to have a typical yj star, right? So here's our yj star. And we want to know what the bounds are on x. So we know what our what the limits on xk star have to be. Okay? So the limits are what? Well, the limits are we go from here to here, and we know that x squared plus y squared over 4 has to equal this. Now if we've got a yj star, it should be pretty clear that down here x equals, well, let's just do it, x plus yj star squared over 4 has to equal 1 minus zi star squared, and I didn't leave myself enough room to write that, over 9. We understand what that is, right? And it follows then that and that's x squared. X equals plus or minus the square root of 1 minus zi star squared over 9. That didn't leave myself enough room again. But then that's going to be minus yj star squared over 4. Okay? And of course, one of the points, the point for the plus is here, and the point for the minus is here. And those are the points on the curve. So that your x values have to be from here to here, and you're going to have to partition that interval. So now we have negative square root of 1 minus, we'll do z squared over 9 minus y squared over 4 equals y naught, but it's not just y naught, okay? Because we've got an I and a j here, it's got to be y naught j, okay? This part of the partition is specified, and I should say, and you know, I'm going to have to back up and fix this. I'm a step ahead of where I should be. Okay? So let's back up and insert that step.